Okay, this is my presentation on the periodic table. I hope that besides informing you on some things, I can teach you more about this idea that is central to chemistry. We will start with the history of the periodic table. Most of the credit for the table goes to Dmitry Mendeleev, however you want to say it, the so-called father of the periodic table, although he was not the first one to notice elements could be grouped. We start with Antoine Lavoisier, who was the first to realize the elements could be grouped into categories based on their properties. In 1789, he grouped the known elements into gases, nonmetals, metals, and earths. Another scientist performed a similar experiment in 1829. Johann Dober, I can't tell what the names are because they're confusing in Iner, realized groups of elements that had similar properties could be grouped into triads. He also realized something very important. In the triads of elements with the similar properties, he realized he could predict the middle element's properties from the properties of the two outside ones. One such triad would be lithium, sodium, and potassium. This is very useful to the next set of facts I'll be giving you later about Mendeleev. Next, we head to France to visit the discoveries of Alexandre-Émile Beguier de Chantecourtois. He was a geologist, but scientists back then did not specialize as much as they do today. He created the vis tellurique, or telluric screw, and this was a early form of periodic classification that used a three-dimensional arrangement of the elements. His ideas are what brought this next topic, the actual periodic table, into fruition with Dmitry Mendeleev. He brought it all together. He discovered the periodic system, or periodic table, as he called it the periodic system, in the winter of 1869. He did so by writing the names and properties of elements on cards and arranging them in different ways. When he arranged them in order of increasing atomic weight, he figured out that certain types of elements reoccurred. For example, a reactive nonmetal was always followed by a reactive light metal and then a less reactive light metal. He was also able to leave gaps for undiscovered elements and correctly predict their properties, which is very impressive. And then within the next 15 years, 3 of these elements were discovered, and Mendeleev's and his claims were proven very accurate, which is pretty awesome. There was a slight hiccup in the 1890s when the noble gases were found, and they seemed to contradict his work. But actually, these work out and fit in as the last group on the table, giving it a periodicity or a periodic interval of 8, which is pretty crazy. This next picture, slide picture, whatever, is a picture of a modern periodic table. I will go over its arrangement in the following slides, but I wanted to show an unchanged chart first that didn't have any markings or animations or whatever I'm about to throw on it. I don't know, this is in the future, in the past, whatever. You can see the table has a legend or key at the top, which is up on this one specifically, metals, metalloids, and nonmetals, and then the colors on the table. That shows which elements are part of which group. More extensive subgrouping based on states of matter will be shown in the following slides. Next, I wanted to go into what a singular element on the table looks like. This is an example of what a single element looks like on the periodic table. The number at the top is the number of protons the atom has, or the atomic number. This is very important because the elements on the periodic table go in increasing atomic number from left to right. So that's how they're ordered. In the middle, the abbreviation for the name is known as its elemental symbol. For carbon, specifically here, it's just C. Its full name is sometimes placed under it as well, like it is here. For even people new to the idea of the periodic table to understand. The last item on an individual elements section is the atomic weight, which is very important. This is the number of atoms a proton has, plus the number of neutrons it has. The reason it is written as a decimal because the weight is an average of all the element's isotopes, which are basically versions of the element with different amounts of neutrons. Each proton and neutron are 1 AMU, or atomic mass unit. And then for this element, the atomic number is 6. So it's 6 AMU, and then we know that the atomic weight is 12, so 6 minus 12 is 6. So we know that the element has 6 protons and 6 neutrons, making the atomic weight 12. This is the full table I will explain further. The whole table itself is arranged in order of increasing atomic number. The different rows of the periodic table are called periods, and they have a period number on the left. This number tells us the highest energy level an extra electron occupies in that element. They're not there on this chart, but usually they are there. On the other hand, the columns, I'm propping them up now because I forgot to. Oops, I'm sorry. You could see the period across the screen in the middle. But at on the left side, that is a column, and that's called a group. And in a group, every atom every element in a group has the same valence electron configuration, and because of this, they behave in the same way chemically. Then we can go further into groups, and each group on the table has a name, or not each group, each section, or how I want to say it is the colors that are marked on the table, basically. Okay, now we're going to go into the different groups on the table and the different colors and how they respond to the groupings of the elements. So the first one we want to go to is alkali metals. They make up group 1 of the table and comprise lithium through francium. They have very similar behavior and characteristics. Also, hydrogen is group 1, but it exhibits few characteristics of a metal, and it's often categorized with the non-metals, as it is in this one. Secondly, we're going to go to alkaline earth metals, which is the orange on this. They make up the group 2 of the periodic table from beryllium through radium, and they have very high melting points in oxides that have basic alkaline solutions. So this is very important. They also are possibly even more reactive than the alkali metals. So then we'll go on to the transition metals, and they're metals that have that are compromised groups 3 through 12, and the lanthanides and actinides, which are parts of them, but the lanthanides and actinides are also something different. But these are just all of the metals grouped together, just different. It's just all the metals grouped together, basically, like that. I can't say anything more than that. That's just what it is, and they're just metals. And then we go to the lanthanides and actinides, which are grouped together because they would extend the table radically, but also because they are also known as the F elements because they have valence electrons in the F shell. I don't want to go into more of that. That's complicated stuff, but just to let you guys know, that's why they're grouped together at the bottom. The lanthanides comprise elements 57 lanthium, obviously, through 71 lutetium, and the actinides comprise elements 89 actinium, obviously, and then through lawrencium 103, and all of the actinides are radioactive, and only 2 of them occur naturally. So now we're going to go on to our next one, which is the basic metals. These are just parts. These are just metals that are on the table. They're also known as the post-transition metals. They usually have low melting points and they're softer, but they also conduct more poorly than transmission metals, which are great conductors. There's not really much to say about these guys. There's more to say about these next guys, the metalloids. They go through the metalloids contains boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. They behave as semiconductors for like your computers and stuff. And they're also called semi-metals or poor metals because they're not quite metals, but they're also solids. Next, we'll go on to the non-metals, which is a lot of gases, and I'm not sure there's any liquids here. I'm not sure if there is. That's what I meant to say. That includes hydrogen. It's used to classify hydrogen, like I just said. Carbon, nitrogen, phosphorus, oxygen, sulfur, and selenium. These are all very reactive, and they usually react with things in the alkali metal and in the alkali earth metal columns. Basically one side of the table reacts to the opposite side of the table. It's like a parallel thing. It's interesting. But after this, we go on to the halogens, which are a subset of the nonmetals, also gases. They comprise group 17. They're generally very chemically reactive, like the other nonmetals I just listed, and are present in the environment as compounds, not pure elements. So you have to break them apart from their compounds to find them. Like iodine. Iodine's in a lot of things. Iodine's a lot present. So is fluorine and chlorine. But they just need to be broken down from compounds to actually have the pure element. And next we go on to the noble gases, which comprise group 18. Absolutely non-reactive, very stable, exhibit similar properties of being colorless and odorless. They're just there. Maybe they light up cool like the neon signs, but like they're just little guys. They're just chilling. So that was my presentation on the periodic table of elements. I hope you guys learned something today. Thank you so much, and go have some fun, man.